T is the transformation that goes from Rn to Rm. Rn is called the what? Domain. Good. And what's Rm called? Close. The codomain. New word. So T is like, well, yeah. So T sends vectors in Rn to vectors in Rm. Okay? It's just a rule that sends a vector in Rm to a vector in Rm. And so Rm is the place where all the vectors are landing, but you might not have every vector in Rm is something that got sent from Rn. So the range is the set of all stuff that gets sent to Rm, but it might not be all of Rm. So we have two different words, the codomain and the range. The codomain is the whole thing. We'll get a little more into this in class. All right, if x goes to T of x, what is T of x called? Image. What's another name for a transformation? Mapping or function? Revalue? No, it's not. So today we're going to learn about linear transformations, and we'll see that multiplication by a matrix A transforms a vector x into a new vector b. All right, so I sort of broke the reading into three big things. One is, what is a transformation? So transformations from Rn to Rm. Transformation is a rule or a function or a mapping that assigns each vector x in Rn to a vector b in Rm. So this is a function. So we're really just expanding our definition of function here. So we've all had experience with the word function. It's a rule that assigns each x to a specific y. So now instead of assigning x's to y's, we're assigning vectors to other vectors. It's just an extension of our current working knowledge of a function. So before, our inputs and outputs were just real numbers. Plug in one real number, you get a real number, another real number as the output. Now we're plugging in vectors. You plug in one vector, you get another vector as your output. Yes? Transformation is just a word for a function. Oh, no, I don't think so. Yeah. In previous courses, sort of the generic name for a function was f. So our generic name for a transformation is going to be t. And the notation to describe a transformation is that t goes from Rn to Rm. And Rn are the kinds of vectors you plug in. Rm is the kinds of vectors you get out. Or you can define it as x goes to T of x. That little arrow, x becomes T of x. Or is mapped to T of x. Or is transformed into T of x. So we call Rn the domain, all the vectors that you can plug in that go into the transformation, that's the domain. And then the whole space of kinds of vectors you can get out is the codomain. It's not the range, okay? It's just the codomain, because you might not get every vector in Rm as an output from your transformation T. So we call Rm the codomain. So T of x is called the image of x under the action of T. The set of all images is called the range. All possible outputs or images is called the range of T. It's a subset of the codomain. Sometimes it's the whole codomain, sometimes it's smaller. All right, and then after we talk about general transformations, we're going to talk about linear transformations, a special kind of transformation that satisfies these two properties. T of u plus v equals T of u plus T of v. So you can add inputs, then apply the function t, and you get the same thing as if you apply the function t to each input separately and then add the results. And you get the same kind of thing applies with scalar multiplication. You can scale your input, then apply t. You get the same thing as applying t and then scaling. So an example of a simple linear transformation, like something that we've all seen before. We're going to take t that goes from R1 to R1, from the reals to the reals. So this is a kind like a regular old function that we've all talked about before. And we're going to let t of x be 3x. It's just a function, line through the origin. But alternatively, we could write this notation as x transforms to 3 of x, where x becomes 3 of x. So the domain of t is all reals. The codomain of t is also all reals. And the range of t is also all reals, because you can get any real number as the output if you choose an appropriate x. So we can show that this is a linear transformation, because if you choose 3 arbitrary constants, a, b, and c, and you take t of a plus b. Okay? So I'm just going to apply the rule t to the sum of a plus b, and t is just triples things. Okay, so t of a plus b is 3 times a plus b, and then you can use this distributive property and you get 3a plus 3b. T of a plus t of b is 3a plus 3b, so t of a plus b is the same as t of a plus t of b. That? Yes. Sorry. Okay. And then the same thing with scalar multiplication. So if I want to do t of c times a, that's 3 times ca, right? Because that's just the rule, t triple stuff. So plug a ca into 3x, and you get 3 times ca, which is the same thing as c times 3a. That's the associative property of multiplication. And then if you do c times t of a, you get c times 3a, so they're the same. And now we'll look at a simple nonlinear transformation. Again, we'll just go from R1 to R1. If t of x equals x squared, then the domain of t is R. You can plug any R value into t. The codomain is also R, but the range of t is just positives, right? Because when you square stuff, you only get positives. So that's the difference between codomain and range. So t goes from R to R, meaning the inputs are real numbers and the outputs are real numbers. But the range is not all of the real numbers. It's just this subset of positive reals. And this guy is nonlinear because, again, we're going to take constants a, b, and c. If I want to apply my rule t to a sum of 2 constants, t squares stuff, right? T is x squared. So t of a plus b is a plus b squared, which is a squared plus 2ab plus b squared. T of a plus t of b is just a squared plus b squared. They're not the same, right? T of a plus b gives something different than just t of a plus t of b. They're not the same, so this thing is nonlinear. I don't even have to look at the other piece of the definition because it has to satisfy both to be linear. And if t is a linear transformation, 0 always has to get mapped to 0. T will have to get mapped to 0 in order to hold this sum thing. Yeah, yeah. That is a great question. We call that thing linear up until today, right? Up through calculus, we would call y equals 3x plus 5 a linear function. Oh, I understand something extreme happened. Because no. We call that thing a linear function because its graph looks like a line. But now we're being much more specific about what we mean by a linear transformation, and that, you're right, would not satisfy it. And I have an example in your activities to do that. All right, so we've got general transformations, linear transformations, matrix transformations. So we're going to treat matrix multiplication as a transformation where the inputs are vectors, and then you multiply each input by some matrix. That's going to be the function. Take an input, a vector as an input, multiply it by a matrix A, and you get an output vector. So every matrix transformation is a linear transformation. And if A is m by n, the input vectors have to be n by 1 to be able to multiply by an m by n matrix. And the output vectors are the b's, and they're going to be m by 1. They're going to have m entries. So the domain will be Rn, the codomain will be Rm, and the range is the set of all vectors B such that Ax equals B has a solution, right? All the vectors that you can get by multiplying a vector by A. That is the set of all linear combinations of A. That is the span of the columns of A. All right, so let's do some work with this. All right, so I've got a matrix A, and I'm going to define a transformation T that takes a vector x and sends it to A times x. So the inputs are going to be vectors, and the outputs are going to be A times that vector, which will give a new vector. Is T a linear transformation? Yes. So linear transformations all have this property that T of 0 is 0, but just because T of 0 is 0 doesn't make it linear. It's like not enough to be linear. Right. So I'm saying the 0 vector, a vector full of zeros. Yeah. Yes. No, they're just matrices. Just nope. So let's go back here. Read that sentence. Every matrix transformation is a linear transformation from the reading. So is this a linear transformation? Yes. Okay, what is the domain of this transformation T? What kinds of vectors can we multiply by A? What are the dimensions of vectors that can be multiplied by A? R2. So that means that I am going to do 1, 2, 0, 0, 4, 0. Can I do that? If I take the row 1, 2, 0 and turn it and lay it on top of the vector, they don't match. Yeah. So my input vectors are going to have 3 entries. So my domain is R3. I can only multiply this matrix by a 3 by 1 vector. Number of columns has to equal the number of entries. All right, so what's the codomain of T? What kind of vectors do I get out of here after I do the multiplication? How many entries do they have? Yeah, Warren, say it again. R2. They'll have 2 entries. Yep, because I'll take this first row and multiply by the vector x1, x2, x3, and you add everything up. So that'll give 1 entry. And then you take the next row and multiply by the vector, and that gives a second entry. I'll get 2 entries out. So my outputs are in R2. So what is the image of 1, 1, 0 under this mapping? So this mapping takes any vector x and sends it to A times x. Right? So 1, 1, 0 is going to get mapped to 1, 0, 2, 4, 0, 0 times 1, 1, 0. Okay, so every vector in R3 gets mapped to A times it. And we just do this multiplication. And you take the first row, 1, 2, 0, multiply by your vector, 1, 1, 0. Things that line up, you multiply, and then you add them. So this is 1 times 1 plus 2 times 1 plus 0 times 0. is my first entry. And then you go to the next row to get your next entry, pick up that whole row, turn it 90 degrees, put it on top of the vector. Things that line up, you multiply. So I have 0 times 1 plus 4 times 1 plus 0 times 0. So my output vector is going to be 3, 4. So if I input 1, 1, 0, it gets mapped to 3, 4 by the matrix transformation A times X. So I put something in from R3, I get something out in R2. Are there any other vectors that have this same image? Are there any other vectors that would get mapped to 3, 4? That I could multiply A by it and also get 3, 4? Sure, I could. Yeah, I could say 1, 0, 1, 2, 0, 0, 4, 0. I want to find out what kinds of vectors give me 3, 4. Right. And I want to see if 1, 1, 0 is a unique solution to this problem, right? Or are there multiple vectors? How do you solve that thing? Augmented matrix and row reduce it. I'll have my calculator do it. You think it's what? You think it's the only one? Well, we'll see. Okay, so let's see, I go into matrix. My augmented matrix is going to be 2 rows by 4 columns because I'm going to augment with the 3, 4. So edit, I've got 2 by 4 and 1, 2, 0, 3 and 0, 4, 0, 4. Quit, go back into matrix, math, I want RREF, back into matrix, choose matrix A. So I get x2 has to be 1, x1 has to be 1. What does this thing tell me about x3? It's free. I can make the third entry anything, and I'll still have a solution to this system. So this tells me that x1 has to be 1, x2 has to be 1, but x3 is free. So another vector that would give me 3, 4 would be like 1, 1, 10, right? Or 1, 1, anything would produce the output of 3, 4. Right? So if this were a star instead of a 0, when I do the multiplication, I would have 1 times 1, 2 times 1, 0 times star. And then in the next row, I'd have 0 times 1, 4 times 1, and 0 times star. So I would still have 0 and 0 here, wouldn't change anything. So there are other vectors that have this same image. 1, 1, 0 was not a unique solution. All right, what if I want to find a vector whose image is 1, 1? What would I do? Yeah, I would make an augmented matrix and row reduce it. So I'm looking for a vector that when I multiply A by it, x1, x2, x3, looking for a vector whose image is 1, 1. So that the output is 1, 1. So I'm just going to make a row, an augmented matrix, row reduce it. I have 1, 0, 2, 4, 0, 0, 1, 1. Do this on my calculator again. So all I have to do is change my last column, my augmented matrix, to 1, 1. and redo my RREF, and I get 1, 0, 0, 1, 0, 0, 1/2, 1/4. And that means, again, x3 is free. So the vectors whose image is 1, 1 are going to look like x1 is a half, x2 is a fourth, x3 can be anything. Any vector that looks like that will produce an image of 1, 1. Yeah. Is that good? All right, if I ask you if 812 is in the range of T, it's definitely in the codomain because the codomain is all of R2. If I ask you if it's in the range of T, I'm asking, is there a vector that produces this image? Right? So it's the same question as F, right? Exact same question as F. So go ahead and answer that. We'll go over it in a minute. Okay, so asking if 812 is in the range is equivalent to asking, is there a vector x1, x2, x3 that gets mapped to 812 by matrix multiplication? Okay, so I'm asking, is 1, 0, 2, 4, 0, 0, is there a solution? Is there a vector I can multiply that matrix by that will give me 8, 12? And you could just set up an augmented matrix, row reduce it, and what kind of vectors do you get? Two, three, and free, right? Any vector that looks like this should give you 8, 12 when you multiply it by A. What is H? Oh, what the range of T? Yeah.
Oh, okay.
Yeah. So what is the range of T? So the codomain of T is R2. I'm always producing things in R2. Do I produce all of R2? Can I produce any vector in R2 with this matrix A? Well, you made a mistake then. So can I take this matrix A, and by appropriately choosing a vector in R3, can I create any vector I want in R2? How could you tell? Okay, so we've actually answered this question in a different format before. So I'm saying my matrix is 1, 0, 2, 4, 0, 0. By choosing x1, x2, and x3 appropriately, can I produce any vector b1, b2? Does this thing have a solution for every b1, b2? Yeah, if you set up an augmented matrix for this thing, right. Perfect, Iris, yeah. No matter what the last column of this matrix is, when I row reduce this, I have a pivot in every row, right? So I can just ignore this. Doesn't matter what this says. You know, it'll equal something. But when I row reduce this thing, I'm always going to get, yeah, these guys all reduced to 1, 0, 0, 1, 0, 0. So the A part reduces to 1, 0, 0, 1, 0, 0. And then this will be something and something, right? Some linear combinations of the B's. And I have a pivot in every row, which means that I can produce any B1, B2. So this was a theorem from several classes ago. Pivot in every row. So R2 is the range, yes, because I can produce every vector in R2 by multiplication by A. So AX equals B has a solution for every B. So my range is all of R2. I can produce any vector in R2 as an image of that mapping.